Okay, so thanks everyone for coming to this journal club. We've got some exciting stuff to discuss this week, I think. So we are talking with Huze, who is a CS PhD student at UPenn, advised by James Ski and Jianbo Shi. And he is the winner of Algonauts 2023 challenge, which was this big competition to try and predict fMRI activity from images that were seen in the scanner. So we're going to be discussing his preprint that talks about that approach. And if we have time, we can also talk about this related preprint that he put out about this all-for-one training recipe, which is sort of a take on what can you do with multiple data sets and across subject modeling. So Huze Yang, do you want to just say hi to people?
Hi guys. Thank you for inviting me. It's very excited to share my work.
Yeah, looking forward to talking
Yeah.
about it. Maybe before we get started in talking about the paper, if you just want to give us a little background about how did you get involved in the Algonauts challenge? And like you're coming from a CS background, so like what's kind of the story of you getting involved in this?
Yeah. I come from a CS background, but I've been working on brain-related topic like functional connectivity or is structural connectivity, just connectivity in general since like 2019. And I come across the Algonauts 2021 challenge 2 years ago. It was really fun. Like it's open science. People just like we just raise for a higher score, take no matter what it costs, like 1,000 GPU hour or 2,000, it doesn't matter. Yeah, and once the fun started, I just it's like I have this engineering strengths because I have a CS background, but also I have been exploring this brain topic, this brain encoding model topic for this is my third year on this topic. So yeah, I have actually done a lot in actually all my work like in these 3 years all about brain encoding model and trying different crazy stuff like more ensemble, more data set, or just for higher score in general.
Yeah, so um, I think it's kind of telling that you've won both this year's and the 2021 challenge, but your strengths are like in CS engineering stuff and maybe less in the, I guess, neuroimaging world. Is that correct to say?
Um, yeah, you can say that. Like I'm
Or
familiar
maybe
with
by
this.
now you've got an expertise in neuroimaging, I suppose.
Yeah, like 2 years ago, the 2021 challenge, that was purely brute force. Like I just made a giant soup of model ensemble, but everybody is running a budget. But this year, I can feel that everybody is running a giant brute force. That's what pushed me to like find something else.
Yeah, cool. So let me just explain the format of how the journal club works. So we don't have slides. This isn't a formal presentation kind of thing. Instead, I will screen share the paper that we're talking about and sort of guide, like walking us through some of the like main topics of it for discussion. But the real hope here is that this is kind of an active, open discussion and that anybody is more than encouraged to interrupt me, to ask questions, add comments, whatever. So please be I'm very happy for people to interrupt at any time. Please interrupt using the mic. So interrupt by enabling your mic and just talking. I don't have my Zoom chat open. but if you don't have your mic available, you can still type anything in the Zoom chat and maybe somebody else can vocalize those comments and questions so that we can talk about it. So hopefully, like as we're going through the paper, questions come up, people can talk about their thoughts. And the hope is that Huze can then clarify misunderstandings. As I'm going through the paper, I'm probably going to make mistakes in summarizing things. So please also interrupt me to clarify anything that I'm not correctly discussing. For the people who maybe are not familiar with Algonauts, this is a challenge that is put forth every 2 years by people well known in cognitive neuroscience. So this year, and it's also consistently about trying to build the best encoding models. So this year was trying to predict fMRI activity from scene images using the natural scenes data set. This is a large scale fMRI data set where there were 8 people, 8 subjects who each spent 30 to 40 hours in the MRI looking at static images one at a time. And so the challenge is that they held out a portion of that data set for this competition, and they released the images for that held out test portion. And the challenge is to use those images to predict what was the corresponding brain activity for the subjects. And then whoever wins, there's like a monetary prize, and you can give a talk at the CCN conference. So and 2 years ago, there was also a similar challenge using video. So Hugh's team did a great job and won by quite a large margin. So he put out a preprint discussing what was that approach, and that's what we'll be talking about today. So there is a lot of stuff to talk about in between this paper and the other paper. So I'm just kind of going to jump around and talk about in like particular stuff about these papers. And again, please interrupt me whenever you'd like to like talk more specifically about things. But one of the major things about this memory encoding model was the fact that using memory was really helpful in getting better predictions. So specifically using the last like 2 minutes of signal or the last 32 images that were seen, and use that as additional information to predict the current brain activity for the scene image. There are also a lot of other things that are being used, but that was one of like the big main takeaways that I think has a lot of impacts for other research in fMRI. In particular, looking at this figure 2, this is a brain map where the hemispheres got flattened out. And so like where my cursor is here, this is early visual cortex. And the people who released the natural scenes data set, they have these calculated noise ceilings where this is calculated as every image was seen 3 times. The idea is that if you see the same image again, then ideally the brain activity should be the same because you're looking at the same thing. And so that would be classified as signal. And then there's all sorts of noise in fMRI like motion and scanner drift and all sorts of stuff that you can't really control. And so this is kind of giving you a ceiling estimate for it's impossible to predict the brain 100%. So let's kind of scale that accuracy based on how well the brain activity was the same across repetitions. And so the ceiling is higher for early visual cortex, which is assumedly maybe easier to predict or had more reliable, at least, repetitions. But as seen in this figure, using this model with memory and everything, the performance is exceeding the noise ceiling, especially outside early visual regions. And this is the explanation, to my understanding, is that this is because the noise ceiling is calculated as just how similar is the activation across repetitions and not considering memory, or like basically memory is modeled as noise. And so you're actually able to outperform noise ceiling across most of cortex by leveraging these other sources of signal. And you can compare the relative improvements between these two figures because the baseline didn't include the memory aspect. So clearly memory is doing really heavy lifting in the difference between this. Is that correct? Like the baseline here is the same as this, but there's no memory component?
Yes, the baseline is without any source of extra information, just the data the challenge give us. But the full memory model, if you look at the text on the left column, is both memory and behavior and time. Just this page on the top left. Yeah, here.
Yeah. So are you saying that all three of these are used in the full mem model, but are not used in the baseline?
Yes, that's correct. And if you look at figure 12, there's a model using only the previous frame, but not behavior and time. Yeah, that's the one.
This one.
Yep.
And so that still is doing quite well.
Yeah. Yeah, if you also look at the right column, the time itself is already doing a great job.
And time is, what is time in this? Is this a time elapsed in the scanner, or?
The time is in each image presentation, each trial, they have a run ID. There's a 12 run in a scanning session. Each run lasts for 5 minutes. And they have a trial ID. There's 75 trials in each run. So the time is relative time to this.
To the start of the run?
To both start of the run and the start of this session.
I see. So I guess part of that is like people are getting fatigued across the session.
Yeah, that's it's my guess, but it's kind of like if you ask people to do this for a long time, they get tired or they get sleepy, and also a more a better guess is that we have a clock in the brain. The clock is both modeling the time of the day, and our brain knows the time of its experiment. Like we can count how long has it been, like this 1 hour experiment, how long is it gonna last? And also we can count in this 5 minute run. Like we have a rough idea how long it's gonna last.
Yeah. So maybe it's not just fatigue, but also just kind of expectation of when the run's going to end, and like
Yeah,
cognitively what is the time currently.
yeah, because the brain knows it, so it's in the brain, right? And
Yeah,
you
I
can also say,
suppose.
yeah, you can also say in the left hemisphere motor cortex, um, given only the time, the right column, yes, given only the time, we can predict the left hemisphere motor cortex. So there must be some like left motor cortex is controlling the right hand, and they are using right hand fingers to press a button. So there's some time related pattern of this button press.
Interesting. I guess also, for context for everybody, there was a task for the natural scenes data set. So there's images being presented one at a time. Every image gets presented 3 times total across the up to 40 hours of scanning. So there's obviously many scanning sessions. And the task is to press a button if an image has been presented more than once. So if you recognize the image, it's an old new task, you would press the button. And I also believe there was like a pseudo randomness involved in when there was an old trial. So like it was like somewhat equally spaced across all the sessions that old was coming up. So people couldn't really predict there's an old
Yes.
about to come, right?
So, so their idea is that even in the first ever section, there's old image, and even in the last ever section, there's also new image. But still, even if they add this randomness, in the beginning of this experiment, there's more new image than old image, and in the last few sessions, there's more old image. So we can, if we look at the paper, we can see there's two subjects, subject 6 and 8. They are just guessing for everything is old in the last few sessions.
Oh, really?
That's yeah, that's funny.
Interesting. So I'm guessing their data isn't as predictable.
Um, yes, but that's more complicated than this, because subject 8 is also the subject with the lowest data quality because of head motion and also some I don't know issue. So we can't just say because it has a lower prediction power on this time, it's the time is less predictable for him, for her. We cannot say that because there's no really direct comparison across subjects.
Yeah. I guess like we can look at the prediction powers and see who's able to get predicted the best, but that doesn't necessarily mean like there's a core reason behind it. It could just be that they're fatigued or not paying attention. It could also just be that their brain is harder to decode for whatever reason, I guess.
Yeah, it could just be they're moving the heads in the scanning.
Yeah. All right, so let's talk about the core of how you did this. Like, what is the actual model? And so I think let's spend some time on this figure to see what's going on. So these are 4 inputs that are going to be used to, in this example, predict a single voxel. So coordinates is the 3D position of the voxel that you're trying to predict. Is that right? X, Y, Z?
Yeah, that's
Yeah.
correct.
And then current image is the image that's being viewed. Conditioning is multiple things. So there's behavior, like if they pressed a button, how long it took them to press the button, the response time. There's the time elapsed that you were talking about earlier. There's memory statistics about if you've seen the image before.
Yes, the statistic is that when was this image presented previously, or if if it is an old or new image, and how long has it been? Like even if we say this image was presented 10 items before, but in this 10 items there can be a 5 minutes rest, or there can be a whole day rest. So we need both item and time.
And if it's a new item, does that just mean that there's no conditioning for the statistics or?
No, I feel this new images with a special token, so the model can know it's a new item.
Okay, so does that mean every new image gets the same special tokens?
Yes, that's correct.
Okay. So that's conditioning. And then finally, there's memory images, which is the last 32 images that were seen prior to the current image, right?
Yeah, that's right. Both their image and their conditioning vector.
Right, cool. So yeah, a lot of stuff that gets fed in through the model. So I guess let's kind of work our way through this figure, starting with the current image. So this current image gets fed through a VIT. In this case, this is the Dino V2 pre-trained model, but also it's getting fine-tuned with LoRa. So most of the model's frozen, but you have a couple of these trainable low dimension layers that are able to fine tune the Dyno V2 model. And there's also this conditioning that gets fed through an adaptive layer norm transformer. And that's also getting injected into the VIT, like through those trainable layers.
Yes, so the way we inject this conditional vector is like you inject text prompt into a diffusion model. And people use cross attention these days, but back in the old days, like the GAN, we inject style code into GAN by this adaptive. Before that was called adaptive instance normalization, but nowadays we have transformer, so it's become layer normalization, but still the same idea.
Okay.
Also, the LoRa fine tuning is critical for this adaptive layer normalization to work because it's modifying every layer output.
The adaptive layer norm is modifying the LoRa
Yeah.
layers.
So the adaptive layer normalization idea is that in each layer's output, you shift it with shift every channel with a learned like shift and scale. So this will drift the data little bit by little bit, but in every layer, so that the whole thing gets drifted from one style to another, like GAN days, or in diffusion is generated as a different image.
I see. But sorry, but how exactly is the output of the adaptive layer norm getting fed into the transformer?
Um, I, I have a figure for this if you
Yeah, that's over here, right?
yeah. Yeah, so it's basically fits right after the layer normalization layer. And there's two scale. The first scale is right after layer normalization, and the second scale is right after the attention layer or the MLP layer. Uh, so I didn't do any ablation study for this or do any comparison. Like the simplest way people inject behavior data into this image is just by expand the image channel and concatenate the expanded behavior data into the image channel. But I guess this way is more like computational efficient, or just it's injecting into every layer of this backbone. But if you just concatenate the whole thing to the input image, it's only affecting the first few layers. And this thing can be like drifted out in the later layers. So people also do concatenate this behavior data for the later layers. But it's the same idea as this adaptive layer normalization. Just inject the information to every layer of this backbone VIT.
Okay. And what is the input tokens?
That's an image. So each image is a 16 by 16 token plus a class token.
Wait, so that's from the Dyno V2 or this is independent?
That's the Dyno V2.
Okay. So Dyno V2 gets used for the adaptive layer normalization too. This all gets fed into every layer of the Dyno V2 that you're fine tuning with LoRa.
Yes.
Okay. And then also there's a subject specific part of this adaptive layer norm.
Yeah, that's because if you look at the behavior data of this subject, like I said, there's two subjects who just keep pressing for old in the later section. So the distribution of this button press will be different from the other guys are actually trying. So
Yeah.
we need a subject specific transform for this.
So you have like subject specific like linear projection or something?
Yeah, so in here, right after this conditioning, there's a MLP layer. So the
Right.
first layer of this MLP is subject specific.
Hmm. I see. Okay. Thanks for explaining. So this leaves us then with where my cursor is. We have this like embedding that'll get fed in, and this gets fed in both through average max pooling, but also through this retina mapper layer selector modules, where my understanding of this is that these are models that you train to be able to convert the XYZ 3D position of the voxel into where it is in the image? Or is this where it
Um,
is in like a latent space of the image?
that's a latent space. So the motivation is just spatially close voxel like V1 voxels or FFA is phase selective voxels. If they are spatially close, they should have similar function. Or like the left and the right brain, they are mapped to the right and left part of this image. So we can just enforce this uh, spatially close voxels to have similar prediction by enforcing the input for them to be similar. So like before we design this Retinotopy module, what people do is that they just take a max pooling or average pooling of this whole latent feature map and feed this to every voxel and do a separate linear regression for every voxel. But that will not give a like big prediction score, especially on early visual, because we know there's some retinotopic mapping in early visual. So this retina mapper is just designed for this early visual voxels. If you look at the second row on the left, the left brain is mapped to the right part of this latent image grid. So the right grid is 16 by 16. That's every token in this Dino V2 VIT. And also the image is upside down because the way our retina works.
Right, but this image coordinate, so this is not actually representing the pixels of the image. This is representing a latent representation of the image.
Yes.
Okay, so yeah, I was wondering why there's like nothing going on where my cursor is, but that's because this is not image space anymore. This is like a latent space.
Yes.
Like, what does it mean if everything is in the center here versus farther out?
If you look at the second row, you can see the center things, they are high level visual cortex or uh, uh, you can see the two visual stream in early visual, they are spread out, but the gray things, they are mostly not. So if things are in the center, it's just DJ, it just go back to the average pooling or max pooling uh, feature selection. Um, I just sent you a video like 1.5 hours ago.
Oh yeah,
That
how
uses
about we
uh,
can take a look at your cool animations. Um, should I open just like this one?
yeah, this one should be good.
Oh, hold on.
Like this one is how this retina mapper and layer selector are learned during the training epochs. And this one is colored. There are four colors: red, green, blue, and purple. They correspond to four candidate layers in this VIT. So we took four layers from this VIT and select one layer for each of these voxel. That's how these dots are colored. So the early visual, they are red, means they are selecting the first layer,
Yeah,
and
or the
the high
earlier
level
layers
stuff.
of Dino, which are assumedly
Y-
like lower level image features, I
y-
guess.
yes, and if you look at the early visual voxels, their distribution on the latent image grid, you can see they are spread out. But the purple stuff, they are clustered in the center because they are more about semantic or the global stuff.
Yeah, but why does semantic global stuff get represented in the center?
Um, they don't have to be in the center. They can also be in the class token. But um, they have to find a place to go in this image grid. If you play this again, you can see they are initialized to the center, and the purple stuff, they're they're trying to move to the peripheral, but then there's not enough like force to move them to the peripheral than the red dots.
But is that because, like, I'm just trying to interpret what it means to be like center versus peripheral in this latent space. Does that mean that there's like more varied signal that can be mapped to the voxels?
Um, uh, Here, the layer selector is used with retina mapper, so that means the purple voxels, they are clustered in the center, but their latent image grid is different from the red voxels because it's a deeper layer.
Oh, so
And in
this
this
is more
deeper
of a
layer,
byproduct of which layer it is.
the right one is both of them is which layer it is. Like they are colored in four colors, correspond to four layers. So um, even if we use only the first layer for all these voxels, the purple stuff or the high visual cortex voxels, they are still in the center because the way this if that's a convolutional neural network, the way it works is that semantic features are in the center because convolution, like when things get convoluted, the center image grid gets more information from the peripherals. But I can say the same thing for the transformer, but this is what we saw here.
I see. And by the way, this animation is super cool. So thanks for
Thanks.
sending that along. Yeah, so the idea here makes a lot of sense, right? Like, and this is what this kind of information often gets used in like retinotopic mapping, population receptive field stuff. Like we know that voxels that are close by other voxels are going to represent stuff similarly, but also that voxels have a receptive field that is specific to portions of the visual field. So maybe a voxel is only going to be receptive to the like upper left of your periphery when looking at something. So it makes sense to try and use that information in some way to better predict the brain. Um, I guess one question then is, did you consider using the, I guess, how does this relate to receptive fields? And did you consider using the population receptive field mapping runs, which would tell you the
Um,
receptive fields of the voxels?
so so if you only use retina mapper without layer selector, it's because we only sample one point from the latent image grid. It's impossible to capture the size of this receptive field size. But we know shallow to deep layers they have bigger receptive field size. So this layer selector is doing the job for the size. The reason we do this is if you think about the alternative, like in the original NSD paper, they are fitting a Gable filter or a free shape attention mask for each voxel, and hopefully that will capture their receptive field location and size. But first, that way is harder to interpret. You don't get this cool like plot or animation, and also that way is much more like if you do a free shape attention mask, you have much more parameters and that overfits. And also that way doesn't enforce the spatially close voxel to have the similar like receptive field. And also that's because I did this in practice, that's too slow. Like if you use a free shape attention mask, you have to do a 256 floating point operation for each voxel. If you add this up to the whole brain, like 300K voxels, you get a 10 times more flops than the backbone VIT. Yeah. And if you do this 1 point sampling, you only get like 3/4 of the backbone VIT's computation.
So it can prevent overfitting, but also it's still kind of a limitation that you can't have a sort of receptive field size information.
Yes, I'm hoping this layer selector will capture this receptive field size information, and looks like in practice they did. Like we can see early visual to higher level
Yeah,
voxels they
that's
are
true.
selecting different layers.
Yeah.
But this is still like less degree of freedom than fitting a free shape attention mask. Or you can you can you can improve this free shape attention mask, make it condition on the coordinates. But still that's a lot of computation.
Does anyone have questions at this point regarding the retina mapper, layer selector, or the VIT stuff that we've talked about so far, or anything so far?
Hello, I just have a simple question.
Go ahead.
Okay, so I was wondering that when you were talking about the subject information in the first layer of the MLP, so what exactly is the information that you feed to the network regarding the subjects?
Sorry, say that again. What information?
Yeah, because you mentioned earlier that the first layer of the MLP is related to the subject.
Yes.
So when you say it
Oh,
is related to the subject, so what kind of information do you feed to the network for the subjects?
so I have a separate first layer for each of the subjects. So the input for this first layer they don't have a spatial token for each subject, but it's just the whole first layer is different for each subject. Like I have in my implementation, I have an indexing model. Each subject will select the model for them in this first layer. You can also do like a special token for each of the subjects, but like they work the same, I guess.
Okay. So while training the network, you are obviously not using all the subjects data, right? I mean, you must be keeping some subjects in the held out data set or the model.
No, we are training with all the subjects. So in each batch, we have a random number of subjects, sometimes 5, sometimes 8. So I will do a forward pass for in this model for each of these subjects and gather all this output and do a gradient backward, because we cannot just simply like forward a batch of different subjects.
Okay. Okay. Thank you.
Thank you.
Yeah, great question. Anyone else have questions to ask at this point?
Just one other question. When you were looking at that video, so there was this question that you were asking that why the purple is in the center and the red is in the peripheral. So I was wondering if it has something to do with the actual representation of these areas in the brain, like how the V1 is on the periphery and the more like the centered area is near the neocortex, like in the brain, the actual mapping of these areas.
Yes, so it's well studied that V1 is doing retinotopy, like the left brain is seeing the right half of this image, and right brain is seeing the left half of this image. But there's also some claims that PPA is seeing the peripheral of this image. Like if we have an image, a person standing on a grass bed, and the PPA is activated by this peripheral grass bed, but not the center person. But here we find PPA is still like centered purple or is blue. So here, the blue, there's some blue spread out in this latent image grid. They are mostly the upper part of this visual string, but not the lower part. If you look at that 2-row image with a different uh, with this with a 2D color bar, so um, so when people study retinotopy, they don't get this kind of scatter plot that map each voxel to the input image grid. Instead, they do is they study for each of this, and they plot on the brain each of this voxel. Um, what's the angle of what's in a polar coordinate system? What's the angle? What's the diameter of this voxels? Voxel map to the input image space, and also they will also show what's a diameter of this receptive field. So here, what I'm showing on the retina mapper is the alternative for this polar coordinate system, and on the right, the layer selector is this diameter of receptive field size for each voxel.
Okay.
Does this answer
Yeah.
your question?
Yes. Thank you so much.
Okay, so that is this part. So then you also have the conditioning get fed into a separate MLP, which is shared across subjects.
Yes, they are the same as the adaptive layer normalization MLP. Their first layer is subject specific and later part is shared. So,
Okay.
so the motivation to have two branch for this conditional vector is that we have some signal that is not image dependent, like the time. The clock is just ticking no matter what the input image is, and there's some depend on the input signal on the input image. Like if I present the same image 2 times, the second time the brain will encode it differently, because the brain can count how many times this image has has been seen. That's the image related part. But
Cool.
I
Yeah.
don't have any experiment for this clam yet.
Yeah, it makes sense. Definitely makes sense
Yeah.
that having a separate part to focus on the conditioning would be useful. And then maybe you can help explain this compress part. So you take the 32 previous images along with their conditioning, and then you compress it. I can bring up your figure for this. So how maybe you can help us understand what this figure is.
So the motivation is to have a image have a latent feature vector that contain all the information about its previous 32 frames. So a straightforward way is we fit each of these 32 image to a VIT and take the final class token and concatenate them. But I want to reduce this dimension from a giant class token to a low dimension. Here is the blue MLP is doing is to reduce the dimension. But also you can notice here the blue MLP also takes the conditional vector as input. So the reason the conditional vector is not injected to the VIT here is because it's expensive to run a VIT end to end for 32 images. And the purple part is time embedding that this MLP needs to know what's the time of this image is being compressed. Because the motivation is if that image is one item ago, the brain should have a stronger signal compared to an image that I say 30 times item ago. And after this compression, I run another orange compression MLP to further reduce this to a 32 item, because once I reduce this dimension, let's say 64, but there's 32 item concatenated with 64 each, it becomes another giant dimension again. So I compress it again.
And then is this the same as the VIT here?
Not exactly the same. The VIT here is a VIT base, but the here the cached VIP is a VIT large, but that's just a minor difference. The major difference is this part is freeze, because if we don't cache them, it's too expensive.
I see. And then why did you say that you only take the CLS token?
Oh yeah, because I was expecting the retinotopy stuff, like the retina mapper and layer selected. They are of minimal importance for this previous image, because um let's say if my guess is that the brain is trying to encode previously seen image, but in this like in this encoding previous image procedure, the brain should not, the retinotopy part of the brain, like the early visual, should not be involved, or is involved less. So it's unnecessary to work here to include this computational heavy retinotopy module.
Oh, yeah, that makes sense. But also, like, you could take more than just the CLS token. You could take like the hidden layer embeddings overall. Why do you only take the class token?
Yeah, so I also, not in this paper, I also did other experiment that compare class token with global average pooling, or just take the whole latent image grid and flatten out. So it turns out class token already works very well.
Interesting. Anyone have questions about the compress module here? So you concatenate everything here together, and then you simply do linear regression at the very end to predict a single voxel. But you also have ROIs, right? So like you're not mapping every voxel independently, right? How does that work?
Yeah. So in this figure, the bottom half, like the VIT, the MLP, the compressing module, and also the retina mapper layers, and everything else is shared across, uh, uh, shared for every voxels. Like I can train for whole brain voxels, or I can train for only early visual voxels, or some kind of ROI. So they will share the backbone weights or lower part in general, but their linear regression weights is not shared. So there's two parts impacting each voxel's prediction. The first part is retina mapper and layer selector is making each voxel select different feature from its backbone. And the second part is this linear regression is not shared across voxels.
I see. You also had like, what was it called? Random ROI ensemble. What is that?
Yeah, it's like um when I'm trying to build a model, I build for each ROI, but we can only have a few, like a handful of predefined ROI with whether by anatomical or functional properties. So I made my random ROI just generate from random, and because I'm making
What
ensemble
is that? Is
anyway.
that like making random brain regions of interest that are like continuous voxels that are next to each other, or is this just randomly picking voxels from anywhere in the
No,
brain?
it looks like a noise. It's a random stuff.
It's like random batches of voxels composing an ROI.
Yeah. So in each of these random ROIs, they contain voxels from all over the brain.
So what's the reasoning behind doing that versus, I don't know, whole brain, everything at once?
Yeah, if you look at on the Offer One paper, I have a comparison for this. So in previous state of the art, like previous Algonauts 2021 challenge, the state of art is people build a model for each of these ROI and combine them, uh, or they passed it. It's a table 3, I guess.
Table 3. Okay.
So table 3, the first column here, naive mix, is what you say if you build a full whole brain model. And last two row, the random ROI S1 is build a S1 means stage 1. There's stage 1, 2, 3 happening in this recipe. So even if stage 1, that is training a separate model for each of these ROI, you can see it's much better compared if you train a giant model for the whole brain. So the motivation is that when you mix these diverse voxels, they have like diverse functionality because they come from different brain regions. So it's more challenging for this backbone model to model them all. So if you separate them out, hopefully they will work better, but that's not always the case. What we find is that if you separate out early visual and late high level cortex, the early visual will get better, but the high level cortex will get worse. So a possible explanation for this is that early visual is providing information for the high level cortex, but the high level cortex does provide anything beneficial for the early visual, but just adds more challenge for this training. So we need to mix these ROIs, and a very naive way to mix these ROI is just dividing them into random ROIs.
And sorry, so if you take the whole brain, like, why is the model not able to learn how to like use this interaction between brain regions as well as when you have less samples?
Yeah, the model is taking advantage of the interaction because we can see the late voxels, they get better when combined with other voxels. But this potential interaction is also making the training more challenging for the early visual voxels.
I
So
see. So it's like a
just
trade-off kind of.
yeah, it's so instead of as finding a best trade-off, what I did is just make an ensemble of everything, like a whole brain model, ROI model, a different ROI model.
And I'm assuming you also compared to like having more informative brain regions, like parcellation based or something that's not just random.
Yeah, I have two postulation based. One is what the challenge provide us. We have anatomical defined ROIs. And the second one is I made my own ROI by doing a clustering of these voxels on the model weights. If you look at figure 2 of this paper or figure 5, yeah, figure 5 is more clear. Figure 6 maybe. Yeah, that's figure 6.
Yeah.
Here is what my ROI looks like. You can see the early visuals, they are blue, and high level, like this model weight ROI is not constrained by spatial proximity. I mean, each voxel can belong to the same ROI even if they are far away. There's no real spatial constraint for them, but they still show some spatial proximity.
Yeah. So, I mean, this is kind of, I guess now we're kind of getting into the all for one paper, but this is, to my knowledge, like a totally novel approach of trying to do shared subject or even shared modality modeling, right? Like you're like these are ROIs that you're finding yourself by basically like k-means clustering weights of specific subjects and trying to put them into the I don't really know the specifics of this. You talk about dendrograms and like hierarchical clustering, which sounds quite complicated. Um, but maybe like, can you tell me a little bit about what you've found with this approach of shared subject modeling, and it wasn't, why didn't you use it for the Algonauts challenge? Because it doesn't look like you talk about it for that.
Yeah, so if you look at the table 3, we just saw after all this hard work, dividing voxels into ROIs and training for each ROI and combined training for other ROIs, you can see here the VE ROI is the ROI I did by clustering, and the random ROI is just the random generated stuff. It only works like 0.003 point better compared to this random ROI stuff. It's still better. If you look at NSD noise normalized score, like the most right column is roughly the challenge score here. You can see it's still a 1 point increase. But the computation cost for this whole procedure, dividing into ROI, train for each ROI, and combine them with a big model for each ROI, I can train 3 random ROI models for each of this one I made it VROI model. So in this Algonauts challenge, it's not about getting a comprehensive one model, but it's only about getting a higher score, right? So in this all for one paper, what I'm trying to do is getting one like, comprehensive model. But the Algonauts model is impossible to distill them into one model. you can see my result after distillation, performance gets worse by 4 score.
Yeah. So basically, all for one is showing an approach to get a unified model, but in practice, you get better performance by having separate models and having the special voxel encoding ROI didn't help that much.
I mean, the all for one approach is unparalleled with this ROI ensemble stuff, because here I'm only using one atlas, but in the Algonaut challenge, I'm trying to use as much atlas as I can. So in theory, I can do this all for one for each of these atlas, but that's too expensive.
Mm. Sorry, does anyone have questions? I guess for the all for one, you're using all these different data sets, right? Like you have this approach of trying to consolidate across even different modalities, like having EEG and MEG, and like,
Yeah.
does that help? Are you able to predict subject one of NSD better, given that you're now able to train with data from other data sets other than NSD?
So it helped a little bit, like in NSD, that's 1 or 2 points increase. I would not say it's a big increase, because for NSD it's a small increase, but for all these small data set like the SINS, EEG, MEG, or HCP, LG data set, they get a big increase. If you look at the figure 1,
Yeah.
so
Yeah.
I
This one,
pre-trained
right?
this model on 5 data sets, and I have 2 holdout data sets. And this is figure 2, is figure 1 on the top.
Oh, yeah.
Yeah. So after training on these 5 data set from different modalities, I fine-tune this image backbone. Like, I'm basically trying to train us same thing as the backbone part of LXN or Dino V2 stuff. Yeah, because neuroscience people just take a LXN and take their feature map and do a PCA and do a linear regression. Here I'm trying to do the same thing, but for this all for one model, you can see in this 2 holdout data sets, it's get a even better score than the Dino V2. So in practice, the result is for NSD we get minimal increase, because NSD is getting dragged back by all these other data sets. But all these other data sets is getting pushed up by NSD for whole like 5 or 6 points. And if you train your model on NSD and fine tune to this small data set, you get a much better score.
So it's really helpful for the relatively worse data sets in terms of like NSD has the highest signal to noise and also the most samples. So NSD doesn't benefit as much, but all the other ones do.
Yeah.
Is that right?
Yeah, so the all for one recipe is, if we don't use the all for one recipe, just simply mix them, NSD will get a lower score. But after using this all for one recipe, it's guaranteed nothing gets a lower score.
Okay, so I guess that explains why not all of the stuff in this paper got used for the Algonauts preprint.
Yeah, and also one biggest factor is that in this paper, I'm assuming like we only take input the current image, because
Right.
it is all other data sets are missing all this stuff.
Yeah, I mean, I guess you
Like,
could use that, right? you can use the conditionings from the other data sets if they have it?
For both 5,000, I guess we have it, but it's a different task. Like both 5,000 is asking the subject to judge whether if they like the presented image.
Right. But there's other
And
stuff like time in the run and like,
yes, we also have that, but they are a completely different experiment design. Like in USD, each image is presented 3 seconds following 1 second blank, but both 5,000 is 1 second image plus 9 seconds blank.
mhm.
And there's blank trials on average, every 10 trials, there's a completely 4 second blank in NSD, but in both sides, both 5,000, there's no such blank.
Right. I guess it's not really something that you can combine across.
Yeah, but um, so I really don't have, after I figure out, I try using other like input like memory behavior time is working so well. I haven't had a time to combine other data set yet.
Do you have plans for combining data sets?
Not really. We have bigger issue like the data preprocessing issue to deal with.
Yeah. Okay, so it's already been an hour, so I don't know if you have time commitments, so you have to head out. There are a couple other stuff we could discuss, so it's kind of up to you.
Uh, I, I, I have to go in 20 minutes, but it's fine until then.
Okay, maybe then, if it's okay with you, we can briefly talk about the actual kind of theory that you have with this paper. So
Yeah,
if you want to go through what you mean by this figure and the sort of theory of memory replay.
yeah. Uh, before this, let me. This is a controversial theory. Like it's only its baby form, and the proof is getting destroyed by myself just a week ago. So anyway, it's still a nice looking theory. Let me get into it. So if we look at the left part, we have a visual input, that's an image of a flower. So alongside this visual input, the brain is also trying to read from hippocampus, the yellow part, and uh, decoded a house. So the brain then combine this flower image with this house image into a single slot. Like in this working memory, we have a limited amount of slots, like 6 or 7 slots. That's average for a normal person. So the brain is trying to combine this uh, currently same image with memory image, compress them to fit in a single slot. And this way, the working memory can store much more information compared to like a single image take a single slot. Because in this task, the subjects they are asked to judge if they have seen this image before. This requires their working memory to contain as much information about the past as possible. So, uh, and also the purple stuff also need to be stored in the hippocampus to be loaded later. So if there's other visual input like a cat come in and hippocampus read flower house, then it becomes cat flower house. But the house will fade away because each time it's compressed, the information gets halved. Let's say halved, because when you combine this blue with red stuff, the blue will take the major part and the red will take a small part. And over time, this information about the house fade away. But this model is only able to capture like still short-term memory. There's no long-term memory happening. Like if things happened a year ago, we as human brain, we are still able to recall that event, but here it's obviously not there. And this theory was backed by my experiment at the time of writing this paper, because we find a previously presented image has a periodicity signal on the brain. But later, this evidence was destroyed by ourselves. We found out it's not the actual image, not the actual content of this previously presented image has this information, but the information comes from the blank images. Like if we input the whole sequence of past 32 images to the brain, there's the brain then the model then can tell how long has it been since previous blank, because the brain is counting how many image has been seen since previous blank. So if we remove this blank information, let's say replace this blank with a random image, so the model won't be able to tell how many items since last blank. Then
What is
the
blank in this?
so in the NSD experiment design, they have in each one they have 75 image, and every other 10 image, on average, every other 10 image, they will have a blank trial. Like a whole blank image lasts for 4 seconds. So my guess is that over time, the subject developed like a clock for these 10 items. Subject is expecting the next blank. So just by removing this blank information, the proof for evidence for this theory just gets destroyed. So yeah, but still, the past image 3 to 5, the past 1 to 5 images still have a considerable amount of prediction power, because one, there's residual from this hemodynamic response function, and two, this information is actually still in the brain. Like the brain is still, whether they are in working memory or the brain is still thinking about it. But there's no this cool periodicity stuff after destroying the blank information.
Yeah. Interesting.
Yeah.
I think it's still a cool like idea of the interactions going on with hippocampus, even if there isn't like a periodicity to it. Like clearly there's memory involvement to a bigger degree than was currently thought of by neuroscientists. Like the residual information is being kept up for a longer time span.
Yeah. So
Like for neuroscientists out there, they need to be like not averaging image repetitions. They need to be, not just doing single trial, but take into account the context of the past 2 minutes of recording or whatever.
Yeah. This like if you only take the current image, you're like trying to solve a problem with handcuff on your hand.
Yeah.
But still, average over repetition is kind of destroying this previous trial information, because if you have, let's say, over 100 repetitions, it just cancel out.
Yeah.
But there's still some parts that doesn't cancel out. Like the brain is counting for how many times this image is presented, like 1, 2, 3, 4, 5. If you average them, you don't cancel out, you add them up.
Yeah. I'm assuming this is like a computationally infeasible thing, but why 2 minutes? Can you make it like the full totality of the experiment thus far as the context? Do you think
the
more
maximum
than
I can go
33 would
is
help?
the maximum I can go is 5 minutes. Like each trial is 5 minutes. between each trial, there's a random amount of resting time. Because in practice, when capturing this data, they will ask the subject, do you need a rest every 5 minutes? So we don't know what happened during this rest.
Does it help to have 5 minutes versus 2 minutes?
In my new experiments, no. Like we only need past 8 frames, plus this blank information. If it's only 8 frames, the information about the blank will not be enough, because there's a blank every on average 10 items. So if we have 20 like previous image, we can know what happened to the previous 2 blank slots.
Mm-hmm.
But the actual prediction power of this image content itself fade away after five item. That's 20 seconds.
After 20 seconds, but it helps the model to have more than 20 seconds of context for the memory images.
It helps by providing information about the blank, but not the content of this image itself.
So if there wasn't blank, then you think that having the past 32 images wouldn't actually help compared to 8 images?
Yeah, I actually have experiment for this. I'm revising this paper very soon. I compared like 2, 4, 8, 16, or 32 after removing this blank information. And we see the performance is diminishing after 16.
Oh, very cool. I'll look forward to reading that. This is obviously super exciting stuff, and I think it makes sense for me to shut up at this point and just end things with Q&A from anyone in the audience. Or I guess there's no questions from the audience? From anyone in chat?
Sure, I'll throw one in. Just curious overall, what has been, I guess, the hardest part of your approach to this Algonauts challenge?
Yeah, the hardest part. That's so in total, I have 50K lines of code, but like before I realized we should use additional information, I already tried a lot of stupid stuff, like searching through a lot of backbones and searching through a lot of model design. But still, the sheer amount of power in this year is just brute force. My brute force is not obviously not leading to the first place. So after I have coded like 30K lines of code just trying this brute force search, then I realized we should use additional information. So the single longest code file is the prepare data from the original NSD repository file. Because yeah, that's 3,100 line of code just preparing the data, but the model itself is only like hundreds of lines. And after that, I still search through a lot of how do we use this information. For example, we have a reaction time of the subject, but over time, like in the first few sections, the subject reacts faster because they just react everything to new, and over time, they turn to think about the decision more. So we need to do some feature engineering on this behavior data reaction time. And I tried a lot of feature engineering stuff. And then that's the part designing this model, we have to think about the computational cost and like the computation cost for retina mapper layer selector. For the retina mapper, I also tried multi-points mapping, but it's just too slow. And also memory compression module, I also tried like, do we use a bigger model, do we use a smaller model, end-to-end or cached, or and it took some tries to figure out we have to have a time embedding or subject specific embedding, this kind of stuff. But like it was fun. Like you have a leaderboard pushing forward. That's the best part.
Wow, that's really
Uh,
impressive, crazy. So yeah, thanks for sharing.
Okay, I guess we'll wrap up then if nobody else has final questions. But yeah, this was super amazing to discuss through, and I think neuroimagers will get a lot of cool ideas for how to process their data as a result of this. So thanks again, Huze, for answering all these questions, walking us through the paper and everything. And thanks everybody for
Thank you for
coming to
organizing.
the Zoom. Hope you have a good time at CCN.
Thank you so much. Bye-bye.
Bye everyone.